Right. Apart from combustion, what was possible for alkenes as the first option, and addition reactions, and we studied a lot of addition reactions, be it hydration or halogenation or hydrogenation. Oxidation is also possible. Now, we're not talking about oxidation in terms of combustions, that's different. But we're talking about oxidation with the help of powerful oxidizing agents. When I use say the phrase powerful oxidizing agent, I hope two specific species come to your mind. One of them is written right in front of you, acidified potassium manganate 7, KMNO4. The other one is K2CR2O7. Now, there is one very specific thing that I'd like to point out. Previously, you have been using both of these oxidizing agents in IGCSE. IGCSE actually was the first class in which you get introduced to these, and you talk about their color changes mostly. You seldomly talk about what they convert into. One, two, you talk about these oxidizing agents and how they are used and what effect they put on the reactants they react with. But sometimes we miss out on very simple small details. So IGCSE is getting stricter by the day, and now they do tend to cut marks on the small pieces of detail. But in A levels, this has been quite a practice. If I say like 2 to 2.5 decades, it won't be wrong. So this small piece of detail I'm circling right now, if you miss this one out, they usually tend to cut marks for it, as well as this one. Now, what we tend to do in IGCSE answers is that we do not pay attention to the tiny pieces of details which are very specific in chemistry. We usually tend to answer our questions, what's the name of the oxidizing agent? You write potassium manganate 7. If you want to be a little bit better, you write KMNO4. That's about it. You never tend to write aqueous solution or whatever. You may give this, you may write this. Both of them are fine, or you may sometimes don't pay attention to the little piece of detail acidified. And I'd like to add over here that we tend to use concentrated H2SO4. At some points, you may use a little bit of dilute H2SO4 for the same purpose, but concentrated H2SO4 is a better choice. So a small portion of concentrated H2SO4 actually gets it activated to act as a powerful oxidizing agent. So whenever we use them, at least most of the time in IGCSE and A levels, we try to go with acidified forms of them. So do not miss out on this tiny piece of detail. You might think it is useless, but in A levels, if you miss out on this piece of detail, you're going to see the marking scheme, especially after 2018, that even highlight or bold the word acidified so that the examiners can cut marks if you miss out on this piece of detail. So don't forget whether you take K2CR207, whether you talk about KMNO4, in both the cases, the small pieces of detail are very important because that's how they are activated, and that's how most of the time, more than 90% of the time in our lab, or what we are dealing with in IGCSE and A levels, we take it in an acidified form. So, moving on, these are the powerful oxidizing agents that we're going to use, but the product that are going to form depends upon the condition we're going to use for the reaction. Now, there are different alkyl groups that are considered in the upcoming portion. It can be R, it can be R1, it can be R2. Now, they all represent alkyl groups, but the way we are going to use R, R1, and R2 are going to make sense because we are going to cater them as different alkyl groups and not the same. Let's start with the practical activity 15.1. This specific thing is in blue color and stated as a practical activity because this is something that we tend to go with in lab. This is something that we expect the students to perform on their own as a part of paper 3 in AS. So that's why it's highlighted like this. Although they can perform hot concentrated acid manganate 7 solution experiments, which are given right below, but they are supposed to perform this one on their own. That's why it's highlighted. So moving on, cold dilute acidified manganate 7 solution. Remember, this is one piece of information or one kind of reactions that we're going to go with. This is the first condition that we're putting. So if it is cold, if it is dilute, the alkene is shaken with a dilute solution of acidified potassium manganate 7 at room temperature. Now the alkene is shaken with. So we are probably talking about a liquid alkene at that point. However, he's giving the reaction for a gaseous alkene, but that really doesn't matter because the reaction goes the same with all of them, whether it's gas or it's liquid. So the pale purple solution turns colorless. However, in some old marking schemes, it might not be colorless, it might be light pink. Now, I hope you understand this point back from IGCSE that both of these colors are acceptable for the conversion of acidified manganese 7 solution upon a reaction with a reducing agent. Now, whatever species it is reacting with, since it's a powerful oxidizing agent, that species can be treated as a reducing agent, but really doesn't matter which species we're talking about here. It's an alkene most of the time. Well, so alkene is converted into a diol. As the name suggests, di means two, ol represents the alcohol, so it's an alcohol with two OH groups to be very exact. Okay, so take a look at this. Ethene is reacting with water in the presence of this. Now, this is the oxidizing agent, which is providing the oxygen. This water is actually representing the dilute part because we have used water to dilute it up, and ethane 1,2-diol. Now, I would like to tell you a couple of things which are not given in the book, but you're definitely going to face them in past papers. So writing those on the book are going to be a good help for you. Now, first things first, I'm going to read the line below so it gives you an idea why we commonly you go for this test. But apart from that, the help for past papers would also be there right after these lines. So this reaction can be used as a test to find out whether a compound is unsaturated. Again, unsaturated means the doubly bonded carbon-based compounds or the triply bonded carbon-based compounds are both going to do that. Now, the decolorization of bromine water is the more commonly used test for unsaturation, but this one is also used. Now, this one back in IGCSE was also given. Here, there, we never considered talking about diols because that wasn't a part of IGCSE. So we stick to the simple piece of detail that the pale purple solution turns colorless. That's about it. That was the boundary line that we drawn back at IGCSE. But here we're going for better understanding, for some deeper learning. So you understand it is going to form a diol, you understand water is a part of the reaction, you understand oxygen is coming out of the oxidizing agent to be a part of it, and that's how we are capable of attaching two OH groups or convert it into a diol. Now, apart from this, what I want you to pay attention to is the fact that whenever we are reacting an alkene with this, let's suppose we're not reacting this alkene, we are reacting this alkene. As an example, I'm picking this one up. So what we are going to do is that you're going to form propane 1,2-diol. Propene, ethene is converted into ethane 1,2-diol. So I'm going to go with names as well as structures to make sure that I make my point completely clear. So this is how it's going to be. OH, OH, and propane 1, 2, diol. Remember, the numbers are separated with commas, and numbers and letters are always separated with hyphens. So it's a pretty good understanding of how or why we have written the name like this. Now, the point I was trying to make is that the OH groups will always be attached to the doubly bonded carbon atoms, and the rest of the structure would remain the same if it's saturated. Now, I would like to make another point. Uh, have you are you done noting it down? Because I'm gonna erase these.
Yes.
Okay, good.
Yeah,
Good.
sure.
So in past papers, though that has been pretty seldom, but uh, even then, I'm gonna discuss it that it doesn't confuse you. So though we haven't been exactly doing alkenes with two double bonds, but I specifically wanted to cater this example. This is 1,3-butadiene, but whenever this kind of stuff is going to react with it, again, you are going to form something similar. But of course, since I've been making the same point over and over again, the doubly bonded carbon atoms are going to be affected by it. So yeah, this is possible. Although this would be a pretty reactive of a compound, and 4 OH groups on 4 straight carbon atoms would be something difficult. But the point I'm trying to make is that if there are more than one double bonds in the structure, all of the doubly bonded carbon atoms would get affected in the same way, having the alcohol groups attached to them. So sometimes there are some past paper questions which have more than one double bond, and you need to cater them in the similar way. I hope I have made my point clear, right?
Yes, sir.
Good. Can I clear this up?
Sure.
Okay. So let's talk about the second condition. The second condition itself is bifurcated into many different parts because when I say the word condition, I'm just talking about the hot concentrated solution. Instead of talking about the cold dilute, we go with the hot concentrate. But under these harsh conditions, the carbon-carbon double bond in alkene is broken completely. Before that, we were never actually breaking the entire double bond. What we were trying to do is that the bond was partially broken and both of the carbon atoms were oxidized in this way. As you can notice, two hydrogen atoms, two hydrogen atoms, so two hydrogen atoms, two hydrogen atoms. When I put it like this, you understand that the single bond in the carbon atom remains the same and the double bond is not completely broken in cold dilute acidified system. But if I talk about the hot concentrated system, this is going to break. And this is then going to further oxidize into different kinds of functional groups. We are going to cater with different functional groups such as ketones or aldehydes or carboxylic acids, or the final product, of course, carbon dioxide, as oxidation would always convert something, a carbon-based compound, at the end of the whole thing into carbon dioxide. The combustion is like a kind of a complete oxidation. Now, these ones are not given in detail. Instead, they are given in notation so that you understand what is going to happen in that case. So, if we have a doubly bonded compound and we have this portion of the structure, means carbon is not elongated with another chain connected to it. Instead, there is just a star by two hydrogen atoms connected to a carbon that would simply be converted into carbon dioxide. Means we're going to break this double bond, and this specific part is going to convert it into this one. Another case, when one of them is a chain and one of them is a hydrogen atom, then the double bond is going to break. This is going to form a bond with oxygen because of the strong oxidizing agent it's reacted with. And this specific functional group or homologous series is known as an aldehyde. This is commonly written as RCHO. We haven't studied aldehydes yet since aldehyde is the last chapter of AS, and that's chapter number 18. But we had an introduction of aldehydes and ketones back in the first chapter. So you have an idea what aldehydes are, but I am trying to put it like this so that when they write the equations and put it like this, you know what the functional group stands for. So this one can be further oxidized, and the oxidation goes on if it stays in the system. If you're not going to take this aldehyde out, this aldehyde would automatically be converted or further oxidized into a carboxylic acid. That's what happens. The R and the carbon double bond oxygen stays over there. However, this H is converted into OH, which completely makes this functional group a different one, and this becomes RCOOH. You might also see in past paper this written as RCO2H, but both mean the same thing, carboxylic acid. So I hope you clearly understand that carbon with one R and with one H, one alkyl group and one hydrogen atom, are stepwise converted from an aldehyde finally into a carboxylic acid. Now, if That's R1 and R2 means these are two alkyl chains. And really, R1 and R2 can be the same alkyl chains or they can be different. They are going to get converted into a ketone, and ketone will not be further oxidized into anything. Now, I'm specifically saying this line because this is something that has been used for paper one for creating a confusion that if an aldehyde, like in the previous case, was converted into a carboxylic acid upon further oxidation, would ketone be converted into something? No, it isn't. So if a structure has two alkyl groups attached to one carbon, the double bond is going to entirely break, and just this portion would be converted into a ketone. Now, we have been continuously considering in these all three case scenarios the one half of the double bond. So whatever is attached to the other half would go accordingly, which means we get to have multiple products. And I'm going to make my point clear since the book caters many examples over here. To see what is formed when we heat to methyl propanene. Now take a look at this. On one side of this carbon-carbon double bond are two hydrogen. Of course, we have just studied this as case scenario one that it would be converted into carbon dioxide. On the other hand, we have two alkyl groups. Luckily, R1 and R2 both are same and both are methyl. So this would be converted into a methyl-methyl based ketone. This part would be converted into carbon dioxide. And of course, there would be some of the water given out. Because the carbon dioxide conversion gives out water, I'm going to go back and show you this. Unfortunately, it's not given over here, but this one is going to give out water on top of it. These two hydrogen will also get to react with the oxygen given out by the oxidizing agent, and this would give water. Actually, this is not written over here, but this is a part of the example. Now, this kind of reaction gives you the idea that what is going to happen with different cases. And really, in past papers, if you're going to go with this exercise, you're going to see many different kinds of doubly bonded compounds. They come up with all different kinds of strategies they can. And with practicing a little bit, this would give you the idea what's going to happen. So if, for example, they go for the vice versa, they tell you what the products are. You can form an alkene imaginary in your mind that might be correct because of what the products are. So, if for example carbon dioxide is given off, you understand that there were two hydrogen atoms to at least one of the doubly bonded carbon atoms. If there was a carboxylic acid, I hope you understand it was the second case scenario, and there was some kind of CH and R base system attached to it. So, what will we summarize? Carbon atom is bonded to two hydrogen atoms, you get a carbon dioxide. And this time he's going with easier examples. Both of them are carbon-carbon doubly bonded, so both of them are converted into carbon dioxide. If both of them are RH systems, they are both converted into aldehydes. And finally, those aldehydes are converted into carboxylic acid. If there is R1, R2, R3, R4 based system, of course, we're going to produce two different ketones, one with R1 and R2, the other one with R3 and R4, since that's the kind of arrangement shown over here. Now, students tend to go with this simple arrangement, and when the past papers, I'm specifically going to quote paper one over here, they come up with slightly different arrangement, the trickier one. For example, they come up with R1, R3, C, double one C, R2, R4, and then they give this kind of option as an answer. They tend to go with this one. Now, you need to be very vigilant that this one is going to come up with R1, R3, C double one O as a separate ketone and R2, R4, C double one O as the other one. So please be very vigilant when you're dealing with these kind of questions. All right. Am I clear
Yes,
with
sir.
this whole thing? This completes
Yes,
oxidation. Okay, great. Because there are going to be some confusing questions related to this one, but if you get them correctly with a few questions, you can be really confident with this one and you can do it correctly. Now, the last part of this chapter, addition polymerization. Now, as soon as I'm going to start with this one, you would clearly understand that this is something that you have studied uh, back in IGCSE. So, yeah, with this addition polymerization section, I would agree that approximately 70 to 80% of what I'm about to go with is something you have studied back in IGCSE, and it's pretty much the same. So, let's get started. We'll get to go with the differences, but for the rest of it, it's going to be the same. Polymer is going to be the long chain molecule, which is would be made up with many repeating units. Those repeating units are commonly known as monomers. For example, up to 10,000 ethene monomers can bond to form a polymer chain of polyethene. Now, this 10,000 gives you a very good idea that N is usually not a small number that we quote in these kind of reactions. Now, we have been using this kind of reactions back in IGCSE. However, some smaller way of writing or easier way of writing is also done in at A level. So both means the same thing pretty much and gives you an idea what is about to happen. Now, this kind of stuff is usually written in at A levels to give you how sophisticated smaller writing would be possible. It also gives you an idea that this whole formula for polythene can be used for some empirical or molecular formulae questions, which you might have already faced for the first 3 to 4 starting chapters practice exercises. Okay, so moving on. Remember, the section of the polymer shown in the brackets is the repeat unit of the polymer. And once you get to know the repeat unit of the polymer in these brackets, intersected brackets especially, so you would be able to convert it into the monomer. And this kind of exercise is something that we have done in back in IGCSE. I don't know whether the teachers sometimes to emphasize on this stuff, sometimes, not most of the time, but you should be capable of converting the monomer into polymer or the polymer back into monomer, even at IGCSE level. So I think, and I'm assuming that you would be capable of doing the same thing at A level easily. This reaction is known as addition polymerization since it's an addition reaction. So that specifies the type of polymerization. The other type you studied back in IGCSE was condensation. That was different and that never gave a single product. Actually, that also gave a simple, small, stable molecule apart from the polymer it formed. So this one is addition polymerization, and it involves the breaking of pi bonds, and usually it converts an unsaturated structure into a saturated bond. So most of the time what you're going to see in addition polymerization is that unsaturated or doubly bond structure would be converted into longer chains of saturated structuring. So propene into polypropene, another example back from IGCSE. Writing it like this gives you an idea of something that we are only doing in A levels. We never used to do that back at IGCSE. So it gives you an idea how this goes. It also gives you an idea that how we're going to put it into a single line as a product and also put the intersected brackets to show that it's a product of addition polymerization. I hope you would be able to convert this into this or this back into this because these kind of questions also exist in past papers, and you are going to notice a few of this sort that how you would be able to convert this into this or vice versa. And MCQ questions related to this are usually a little bit tricky, but once you practice them, it comes easier to you. So this also gives you the idea what the polypropene molecule would look like. Now, if we talk about more about addition polymers, the very next example I'm about to go with is something again that we studied back at IGCSE, chloroethene. However, you never used to call it chloroethene back in IGCSE. We have been using the phrase polyvinyl chloride for this. Since chloroethene is commonly also known as vinyl chloride, and the polymer is then known as polyvinyl chloride. So we have been talking about PVC as a usage for sanitation pipes or gas pipes or guttering pipes. Pipes of those sort are usually made from PVC. That is something that we discussed back in IGCSE. This also gives you an idea how this polychloroethene goes, and the big green colored balls in this entire pollen stick model gives you a very good idea how the structure is repeated in a repeat unit. However, there are many repeat units in this portion. Okay, so in polyalkenes or substitute polyalkenes made up of one type of one monomer, the repeat unit is same as the monomer, except that the carbon-carbon double bond is changed into a single bond. Notice, as in any other addition reaction of alkene, addition polymerization yields only one product. Now, these are some specific rules or boundaries they're setting that it's easier for you to answer the MCQ questions. A few important things. The section of the polymer chain shown inside the square bracket by its structural displayed formula is called its repeat unit. And repeat unit is something that you should practice to convert into a monomer. Instead of taking the whole structure, it's better to always be fast by cutting out a repeat unit and then converting this repeat unit into a monomer. If you try to convert the whole structure directly into a monomer, you might make a mistake. This is a quick tip. It can make you fast along with making you correct. Now, addition polymerization is characterized by monomers which are unsaturated and contain a carbon-carbon double bond, which is later on saturated by breaking double bond into a single bond, and the polymer being the only product of the reaction as I just went through the same line. The portion of disposable of polyalkenes or plastics was considered back in IGCSE, but there were some lines that we used to forget or used to not go with, considering them too easy. Back in IGCSE, they discussed plastic, why plastic was, people grow fond of plastic because of many of their useful properties. They were colored, they were light, they were non-conductors, they were good and easier to use. So that's why we can mold them into many different shapes. So plastics had many possibilities and probabilities of their use or their properties, which were actually advantages in comparison to their other counterparts, either made of metals or something else. So plastics were an immediate success, but after using plastics to a specific time, we understood that plastics are not good if we're going to dispose them off into the landfill sites because the most common and the simplest plastics, like the plastics that we commonly use in bottles, like some of them you can see the mineral water bottles, even they take like 700 years to decompose in a landfill site, and even then, they don't decompose completely, they're just broken down into smaller parts. They still are a source of pollution. So, uh, there were two actual, what we can say, the ways out of this whole pollution system. One was incineration. The specific word was used in just a couple of books back in IGCSE. So it means to burn plastic waste. Now, burning waste was a very good idea if we go like 3 to 4 decades back, because that actually reduced the amount or the size of the waste to nearly one-fifth of it, which seems very lucrative as an option. But once we started why burning wasn't good because it was producing many harmful gases along with it and actually producing a lot of gases which helped global warming. So we are now thinking that burning plastic waste might not be a good idea to save the planet from pollution. So another problem with this one was that recycling companies have separating other plastic waste from polyalkenes. This happens when object must have been thrown away and not sorted according to the recycling codes. So that's why there were the specific codes. And codes is something, when I come to that, you might have seen it in the IGCSE book, we had that kind of triangle that we usually use to draw something like this. Whether we were drawing that triangle. And there were numbers from 1 to all the way 7, showing you what different kinds of numbers stand for different kind of plastic waste. From polyethylene to polypropylene to polyvinyls, all the way to mixture for number 7 were given back in IGCSE book. Because if polychloroethylene is burnt, acidic hydrogen chloride gas would be given off, as well as some toxic compounds called dioxins, which are considered to be carcinogenic. So very high temperature should be used in incinerators to break down any toxins that are commonly produced with it. Now, this is as far as we go for this pollution problem. One last thing, tackling questions on addition polymers. Now, book has this specific portion not because another topic to be taught, but how to deal with the questions I was previously considering for addition polymerization. Now, first kind of question, deducing the repeat unit of an addition polymer for a given monomer. So that was pretty easy. That I explained back in IGCSE as well. Break one of the doubly bonded portions, means let the single bond stay and break the double bond, and just convert it into two single bonds on the other side, which you can actually intersect with the help of brackets. And there you go, you would be able to convert it into a repeat unit. I hope you already know that NS position is also changed. So one kind of questions that you might face. Now, identify the monomers present in a given section of an addition polymer molecule. As soon as you see an addition polymer, you would be able to figure out that it has a repetition in its portion. Now, this is very easy to consider that there are repeat units, right? Now, this should give you the idea of repeat unit. You get the repeat unit, you break these portions, you convert it into a double bond. There you go, you have converted into a monomer. But the ones that were being considered in past papers was somewhat of a difficulty. So what they commonly do in past papers sometimes is that they switch the units around. By that I mean that this one's easy. Why? Because this circular benzene ring is always drawn up top. Now, what they are going to do is that one is on top, the second one, they would switch it around at bottom, the third one is up top, they are going to switch around the fourth one at bottom. To just confuse you. Don't get confused by this trick. The same is going to happen and it would be solved in the same way. I'm going to show you another example. If I go a couple of pages back, the book actually did that cleverly on the previous example of ball and stick model with fluorine. Take a look at this. There is just one fluorine atom in every repeat unit. Now, one repeat unit, two, three, four. Take a look. Fluorine is face downwards, upwards, downwards, upwards, downwards. But these are all the same repeat units. They tend to do this to make it more difficult for you. Don't get confused by this. This still is the same thing, and this still is the catered in the same way. So, getting back to the page we were, actually, that's about it. I thought there was another part to it. Well, that's it.